Welcome everybody to our Bronkhorst podcast. I am Adam Mumford, and today we are going to run a podcast series to talk about how to handle a low flow liquid. The subject is wide, which is why it will be broken down into two parts. And we will have today with us two very special guests. I'm very excited to meet them and learn more about their experience when it comes to handling low flow liquids. And I hope you are too. As always, if you have any questions, you can contact me directly on LinkedIn or via our website at www.bronkhorst.com. Today, we're going to talk about what we consider as low liquid flow and some tips and tricks on how to select the right flow meters with regards to the right application and specific situations. I'll be doing that together today with Ron Tietge, our product manager that you met during our previous series with flow meters for beginners, and also with Allard Overmeen, our global service development manager. Allard's been working for Bronkhorst for 34 years, has great experience. I also mentioned that Ron's been with Bronkhorst for 34 years, so there's 68 years experience between these guys. So let's tap in and see what we can find out with their knowledge. So it's a pleasure to have you on the show, and I can't wait to know more. So before going deeper into the topic with Allard on how to handle a low liquid flow, let's start with the basics. Ron, what is a low liquid flow?
That's a good question, Adam. And well, it's a pleasure to be here, of course, and talk about low liquid flows. And it all depends in which industry you are. And when we talk about the bulk industry, for example, then 500 kilogram per hour is already considered low flow. You talk about research, there it's a lot lower. If you consider that every year they develop literally millions of new liquids, and the ingredients used are often very, very expensive. And therefore, a flow like 100 grams an hour is considered as low flow. And everything less than 5 grams per hour is considered ultra low flow. And as you might remember from the previous podcast, a flow meter is an instrument that measures a mass or a volume flow rate of gas or liquid. And it's possible to control a flow by using a flow controller. And in that case, the flow meter will be combined with a valve or even with a pump if necessary. And coming back on a low or ultra low flow, it's often quite a challenge to get a good and stable flow control.
Yeah, absolutely. And sometimes I think we get lost. We think about high flows as being a challenge, which they are, of course. We know that. But again, on the other end of the scale, when you go down to the bottom end, as you've mentioned, it's sensitivity, it's controlling at low flows, which can sometimes, be an even greater challenge, if not more difficult sometimes. So, I mean, what would you say, Ron, is sort of so typical about low flow situations?
Well, it is a greater challenge indeed. And low flow, or certainly ultra low flow, is very sensitive to the tiniest disturbances in the process, or even in the ambient conditions. And both can have a massive effect on the stability of the flow. And for example, obstruction of particles or gas entrapment or contamination, they can reduce the flow rate. And if your inlet pressure is unstable, the flow will be very unstable as well. So knowledge of the application, as well as a physical transport phenomena of the process, these are essential to deal with the complex matter of low flow handling. And my colleague Allard will tell you much more about this and give you tips and tricks concerning the handling of low flow or ultra low flow.
Yeah. And you've mentioned obviously metering the flow, so that's just pure measurement. And you've also mentioned there, Ron, about controlling the flow rate, which is obviously more of a challenge. Yeah. So what do we use at Bronkhorst as the main sort of principles when it comes to controlling liquids?
Again, it depends on the conditions. If you have enough pressure and you have a very stable pressure, then a valve would be preferable because a valve is more stable than a pump. If you have a stable inlet pressure, of course, and a valve is much faster in response than a pump. On the other hand, if you do not have enough pressure or you are afraid of gas entrapment in your process, then a pump might be the ideal solution. A pump is sucking its own liquid from a vessel or some sort of
tank. We've got customers that are sucking in from IBCs.
True.
Tanks
Absolutely.
that are outside. Yeah.
Yes. then a pump would be preferable because, of course, you don't have the chance of gas entrapment, or at least less chance of gas entrapment.
Ah, get it. Okie dokie. And do you have any examples of different types of low liquid flow handling that you could share with us?
Applications, you mean? Oh, many.
Yeah.
I can talk for hours. I won't do that. Don't be afraid. But our accurate instruments portfolio, as the thermal-based MuFlow and LiquiFlow mass flow meters and controllers, as well as the Coriolis-based mini CorioFlows like the ML120 and the M12 devices, they are absolutely suitable for ultra-low liquid applications. And those instruments for measuring and controlling low liquid flows have proven their use in many applications. To name just a few, investigation of catalysis at high pressure, for example. Low liquid flows of hydrocarbon compounds need to be dosed as stable without any pulsation. And thanks to our Coriolis flow meters combined with a pump, we are able to make this. And if you take labs on a chip, very popular, and other microfluidic devices in pharmaceuticals and biotechnical processes, they significantly reduce the number of chemicals and experimental time compared to traditional means. And it's all possible with our mini CorioFlow series. And there's graphene production. Graphene is a relatively new material with great expectations. It's light, it's transparent, it's flexible, and it has a high electrical conduction, and many applications are foreseen. To name a few, in electronics, for example, or catalysis, or energy storage fields. You have graphene production in R&D or tests in R&D. You need a very stable ultra-low flow. To give an example, one of our customers is using a flow as low as 2 grams an hour of ethanol. This can be done with our thermal MuFlow or with our Coriolis instruments.
Wow. Yeah. Mind-blowing examples there, Ron. It always surprises me where you store all of this knowledge. It's really interesting what you said, because there does seem to be a trend at the moment with customers moving even further down the scale towards low flows. I'll give you an example. Last week, we had a customer who was very interested in controlling flows at 200 milligrams per hour. And wow. Yeah, and we've seen quite a lot here in the UK where people are starting to push the boundaries, and they're looking more at ppm type levels of introduction of liquids. And it's really interesting what you said there, because the MuFlow is something that we often bypass, pardon the pun. And we think about the Coriolis as sometimes being the best solution. But as you've mentioned, the MuFlow, the thermal technology, it really is worth considering for ultra low flows. Very interesting. So thank you, Ron. That's awesome. Now, Allard, how are you doing today?
Hi, Adam. I'm fine. Ron, also thank you for your introduction in this. You asked me to help users of liquid flow fluid systems to get some tips on the stability and performance of their systems. I can give you some recommendations, like that. Working for Bronkhorst for a few decades, starting at Bronkhorst in the liquid department, I learned something through the years. What to do, certainly what not to do when using a liquid. And I can say the smaller you go in flow, the bigger the challenges are to get the flow stable. And of course, when a flow is not stable, a flow is also not accurate. So this is an important thing. And ambient conditions also have an influence on it. But this depends a little bit on what you use. When you use a Coriolis meter, ambient conditions are less influencing. Thermal instruments, word already tells it, it's a thermal measuring principle. Of course, it's depending on temperature of liquids. But you can also get everything, and what to choose is depending on your application. And yeah, we're always willing to help you to find the best solution.
Yeah, I like that, Allard, because what we're looking at is the customer's process, the customer's conditions. What effects can temperature, can the ambient the environment. What effect can that have on the process? And I think that's something that, again, that's overlooked, that should be always considered when looking at the best solution. I mean, so what would you advise, Allard? A Coriolis-based instrument or a thermal-based meter, for example?
Advice in both cases can be the correct advice. It's not an easy question. It depends on different situations. Coriolis, for example, performs very well in a situation where your accuracy is the most important parameter, and flow stability is essential there. And Coriolis instruments can be used on liquids where you do not know the exact physical parameters. Like Ron already explained, more and more liquids are developed through the years. For these liquids, nobody knows, and there's no data sheets where you can say, okay, what are the physical properties of that liquid? So therefore, the Coriolis is a perfect instrument, because the Coriolis measures the real mass of an instrument. So it doesn't matter if you use liquid A or liquid B, the result is the same. It measures the mass of it. Another thing is, for an advantage of Coriolis, is long-term stability. It's been proven in many years that stability for the Coriolis is very consistent. Not saying that the long-term stability of our thermal instruments are bad, completely not. But for the Coriolis, due to the principle, it's better. When you also have a liquid which is a mixture or whatsoever, where it can be that through the time the liquid changes in the process, Coriolis has a big advantage that it also can measure the density of the liquid. So depending on the density of the liquid, the people, certainly in research labs, know what the difference in the fluid is. A disadvantage called of Coriolis is that Coriolis principle works on vibrating of the tube. So when the Coriolis is installed in an area where a lot of vibration is common, like in some production areas where a lot of pumps and everything, you must avoid the frequency of the pump being equal to the frequency of the Coriolis, or you must make sure that you eliminate the environmental vibrations to work correctly with the Coriolis. This can be done with shock observing measurements. We deliver our Coriolis instruments already with a mass plug on it and shock observers to reduce this as much as possible. But if not, thermal mass flow meters can be an option in these conditions, because they are less vulnerable to these conditions. Other thing why sometimes choose a thermal instrument over a Coriolis instrument can be economical costs. When it's used in a process where the process is already known, where we work with known liquids, and the reproducibility of the measurement is a much higher demand as the absolute accuracy, then it can be that a thermal instrument is a better choice. Other thing, certainly when we talk about the bigger flows, big in Bronkhorst terms, then pressure drop over a Coriolis can be an issue. Thermal instruments have less pressure drop at same flow conditions as a Coriolis has. For liquids, that's not a very big option. Sometimes Coriolis instruments are also used for gases, because Coriolis, in difference to a thermal liquid instrument, a Coriolis can be used on both liquids and gases. But when a Coriolis is used on gas, then certainly keep the pressure drop over the instrument in mind.
Okay. I've got really interesting. Thanks, Allard. But from what you've been saying, I've got a couple of very quick questions I hope you can clear up or answer. So we have a lot of customers that like to work in volumetric flows, let's say milliliters per minute, per hour, whatever that might be. How easy is that? Because we're talking a lot here about mass, which is obviously the Coriolis principle. It's pure mass flow, as you've mentioned. But if a customer wants to work in volumetric flow, is that possible?
It is possible. Like I said before, the Coriolis also has the option inside that it measures the density of the liquid. So when having the parameter density and having the parameter mass available in one instrument, it can calculate it itself to a volumetric flow of milliliters. So when customer prefers that to have the flow displayed in volumetric flows, milliliters, liters, it is possible with a Coriolis instrument.
Awesome. Is there any downfalls to that?
Downfalls in it is that this can be used very well with liquid applications. For gas applications, it's not recommended because the accuracy of the density measurement is for gas instruments. Yeah, the accuracy, you can imagine the total accuracy when you have a variation of 1 kilogram per cubic meter in liquid. Liquids have a density which is close to 1,000 kilogram per cubic meter. A gas has a density of only 1 kilogram per cubic meter. So yeah, then for gas instruments, volumetric flow with a Coriolis is not a very good option. But for liquid instruments, it's no problem at all.
Awesome. I think that answers that. Thanks, Allard. My second question there was, obviously, when you're using the thermal principle for measuring the liquid, we need to kind of know, as Ron also mentioned, about all the new liquids that are being manufactured all the time. For the thermal instrument, you need to know about the liquids, so the viscosity, the thermal conductivity, the heat capacity, for example. So for listeners that may be new to this, that don't know the difference between Coriolis instruments, how they're calibrated, and thermal instruments, what is the main difference there? Could you talk a little bit about that?
I can tell a little bit about that. I can tell a lot about it, but it won't be so interesting for most of our customers. In general, it can be said that our instruments in the factory are calibrated on water. And for a Coriolis instrument, it doesn't matter all that much. When you use an instrument and you calibrate it for 1 kilogram of water, and you use a new liquid, a new developed liquid, that 1 kilogram of water equals 1 kilogram of whatever liquid. When you use the thermal instruments, with the thermal instruments are also calibrated on water. And when we use that on another liquid, we have to use a conversion factor. And that conversion factor is, like you said, Adam, based on the density of the fluid, the thermal conductivity, the viscosity, and the heat capacity. In a lot of cases, that's not known. Another thing is that sometimes liquids differ from water so much that the conversion factor becomes a very big number. In that cases, for thermal instruments, we started using calibration on IPA. It's
on beer.
Yes, of course. People in production also need to have some pleasure in their work. No. IPA is what we call the short for isopropyl alcohol. Isopropyl alcohol is an hydrocarbon, and isopropyl alcohol has a conversion factor, to give that as an example, to water, which is already approximately 7 times.
Okay.
And a lot of liquids, like that, it's hydrocarbon. So a lot of liquids have much physical data which are much closer to isopropyl alcohol as to water. Water is the most common liquid in the world, but when you come to physical data of water, water is the most strange liquid we have in the world. It has reasonable big heat capacity compared to all the other liquids. And yeah, therefore, for thermal instruments, sometimes calibration on IPA is the better option. Not said that we never calibrate in Coriolis instruments on IPA, but that most of the time is related to something else, that has to do with the effect that customer liquids sometimes react to water. And then we also completely dry the instrument before sending them out to the customer. But when instrument has been calibrated on IPA, alcohol can be evaporated and dried much easier as water.
I
And
see.
that's one of the reasons why measuring with a thermal instrument gives much more variables possible as when using a Coriolis.
Awesome. That's a fantastic detailed answer to the question there, Allard. And I mean, something you mentioned there, we haven't even started looking at materials compatibility yet, which obviously is something that customers must always consider when purchasing the correct flow meters. And with that in mind, do you have any tips for customers for choosing the correct meter or controller for their process?
Yeah, that's where we come back to when the liquid is not really known or the liquid can vary. When it's a mixture of liquids, best choice is always to go for a Coriolis, because then you can measure the density, you can measure the viscosity of that. You can measure the density of the liquid, and then you have your flow. So another thing is, it's not sometimes that for new liquids the data are not in a data sheet. Sometimes it's also secret, because like Ron said, new liquids are often very special, very expensive, but also used for applications which are still in research phase. And these customers don't want to share this information with us. And then Coriolis, of course, is a better option because it can measure everything independent on physical properties of the liquid.
Awesome. And I think on our website, we also have the product selector tool, which can help you choose the right flow meter or controller based on your process parameters, such as maximum flow rate, operating pressure, operating temperature. So it's definitely worth having a jump on the website and having a look at that first. But as always, it's great for customers to try and size their own instruments, and we feel that's really important for the customer to understand what we can offer. But again, we always advise customers to give us a call, get in contact, because we're also interested in their process, what they're trying to achieve, what is the end goal, because sometimes that can also help us make the correct selection. So that's awesome. Yeah, thanks, Allard. Really appreciate your input. And again, massive thanks for joining us today, Ron. It's been an absolute pleasure. And I hope you guys have also enjoyed it. And if you want to know more, then do not hesitate to get in contact with either myself, Ron, or Allard on LinkedIn. And make sure to follow our Bronkhorst page. And stay tuned for our next podcast. And don't forget to also share this podcast with your colleagues. So until next time, take care, and we'll see you again soon. Bye for now.